Okay, so continuing with our discussion of high availability, we're going to look at some examples on the command line now, where we have router 1 and router 2, which will be simulating our hosts, connected to the access layer of switch 1 and switch 2. Now, switch 1 and switch 2 are going to be running just layer 2 switching to get us up to our distribution layer, switch 3 and switch 4, where our layer 3 routing is going to be configured. So in this particular design, all the interconnecting links between the switches, those will be layer 2 trunks. They're not going to be configured for layer 3 routing. Now, the goal of the first hop redundancy would be that if switch 3 was servicing VLAN 10, so switch 3 is our default gateway for VLAN 10, if this switch goes down, we ideally want switch 4 to be able to take over the forwarding status for that particular segment. Likewise, we'll have switch 4 configured as the active device for VLAN 20. If switch 4 goes down, then we want the active status to go over to switch 3. Now, any three of the redundancy protocols, HSRP, VRRP, or GLBP, will be able to accomplish this functionality for us, but different platforms have different requirements as to, or different shortcomings, I should say, as to what features are supported. A lot of the Catalyst iOS switches will run only HSRP, unless we're looking at like the 6500 and the newer versions. Then it will be able to support the VRRP and GLBP. Most of the routing platforms themselves, like the 3700s, the 3800s, those will support all three of them. So it depends on whether you're running a full iOS router or whether you're running Catalyst iOS. So for our examples today, we will constrain this just to HSRP, but you would be able to take the standby command in the syntax and change it out pretty much exclusively with either the VRRP command or the GLBP command and get the same result. Okay, so take note of this diagram and let's look at the command line to see what the current situation for the topology is. So first, let's look at router 1 and router 2, which will be our end hosts that we are testing with traffic into the network. So on router 1, we have the IP address configured 10.0.0.1, and router 2 has the address 20.0.0.2. Now, each of these devices respectively have the default gateways 10.0.0.254 and 20.0.0.254 configured. So at this point, they do have reachability to each other because the layer 3 switches, which are switch 3 and switch 4, should be routing on their behalf. So I'll have to actually verify this here. Let's see, router 2 should at least be able to reach its gateway. And router 1 should be able to reach its gateway. Let's see if we can reach the other segment. So we have some sort of routing issue between the two routers. So let's go through our full verification of the topology to see what the current state is before we introduce any of the first hop redundancy. So this link on router 1 is connected to switch 1's port fast Ethernet 0/1. So we have this configured just as an access VLAN. So this would be simulating here just our layer 2 access switch. If we look at the show interface trunk output, at this point we have two trunk links. There are interfaces 16 and 19. Those are taking us over to switch 3 and switch 4 respectively. Now if we were to look at the show CDP neighbors, we could correlate interfaces 16 and 19. Those are actually going to those devices. Now we see that VLANs 10 and 20 are allowed and active in the management domain. This means that they are created and they are in the spanning tree forwarding state and not pruned. Now notice that only one of these links is currently being used for forwarding because spanning tree is blocking the other one. It means that port 16 is blocking and port 19 is forwarding. So the traffic is forwarding over to switch 4. If we were to go to switch 4, let's look at the show interface trunk. We have 3 trunk links here. They're interface at 13, 16, and 19, which should be connected to switches 1, 2, and 3, respectively. So if we were to look at the show CDP neighbors, switch 1, 2, 3, that's what we would expect. If we were to look at switch 2, let's look at the show VLAN. We can see that we have VLAN 20 assigned to router 2's port. That's fast Ethernet 0/2. We look at the show interface trunk. We have trunk ports fast Ethernet 16 and 19. And if we show CDP neighbors, these are going to switch 3 and switch 4 respectively. Okay, 16 and 19. Now, up to this point, before we get into our layer 3 routing, what would be a good idea in this type of network design is to check the spanning tree for VLANs 10 and 20 to make sure that everyone agrees on who the root bridge is. Because remember, as we talked about with our basic layer 2 verification, if devices in the VLAN do not agree on who the root bridge is, it means there's some sort of connectivity issue between them. So everyone in the same broadcast domain has to agree on what the spanning tree topology looks like. The topology would be defined there by the root bridge. So first off, on switch 1, let's start with VLAN 10. Let's say show spanning tree for VLAN 10. It says that port fast Ethernet 19 is the root port. Okay, this one is forwarding. This is taking us up to switch 4. We look on switch 4, show spanning tree for VLAN 10. It says our root port is fast Ethernet 16, which is going down to switch 2. So let's go to switch 2. Look at show spanning tree VLAN 10. Okay, so we are the root of the spanning tree. Now, in this particular case, switch 2 is an access switch, so this may not actually be what we would want as the preferred design for the root placement, because we're going to need to make sure that the layer 2 spanning tree topology will agree with the layer 3 routing domain that we are going to overlay on top of it. So when we actually test our failure situations here, we'll look at shutting down a couple different links and how spanning tree and the first hop redundancy protocol together could be in a miscommunication, and we may not actually get the result that we are looking for. And the end result, ideally, is going to be very fast convergence. So now we know who's the root of VLAN 10. Let's make sure also that switch 3 agrees on this. Show spanning tree VLAN 10. It says the root port is fast Ethernet 16. That's going down to switch 2. Okay, so everybody agrees switch 2 is the root for VLAN 10. Now let's look at this for VLAN 20. Assuming that nothing else has been changed, like the costs of the links, it should also be switch 2 that is the root bridge, but it's not. It is switch 4, I believe. Show spanning tree VLAN 20. So for VLAN 20, switch 4 is the root. We can see it has the default priority, 32.768, plus the system ID extension of 20. Probably for VLAN 10, we have a different priority configured. So from our exercises before in spanning tree, I still have some of that left over. Let me take a look at what switch 2's configuration says. Let's say show run include spanning tree. And I have the priority, which is affecting it. So let's remove the manual priority. And we should see now both the root bridge placement for VLAN 10 and for VLAN 20 should fall back to switch 4, because this device has the lowest MAC address of all 4 of them. So again, assuming that the priority is the same on all switches, whoever has the lowest MAC address is going to be the root bridge for the topology. Okay, so now everybody agrees switch 4 is the root for both of these. Okay, now let's look at our layer 3 topology. The hosts, router 1 and router 2, they have basic IP addresses defined, and they have the default gateways set as the .254 address in their VLAN. So router 1 is 10.0.0.1, its gateway is 10.0.0.254. Router 2 is 20.0.0.2 with a gateway of 20.0.0.254. So switch 3 and switch 4, these are the layer 3 switches that will be servicing these. So on switch 3, let's look at the show IP interface brief. Okay, we see that we have VLAN 10 interface and a VLAN 20 interface. Now, since both of these are in the up state, the switch virtual interfaces, that's telling me something else about the layer 2 topology. It's telling me that both VLANs 10 and 20 are in the spanning tree forwarding state, at least on one link. So if spanning tree is not working, the VLAN interfaces would be up, down, or down, down. Up, up, it means that the basic layer 2 topology is working. So we could verify this if we said show spanning tree for VLAN 10 or for VLAN 20. We shouldn't have any issues there. Now, just to be sure, let me check the other routers to make sure I don't have any duplicate addressing. I think these have been cleared of the rest of their config. Okay, so only router 1 and router 2 have their IP addresses. So let's verify this once more. Let's see if the spanning tree placement had anything to do with the connectivity, and it really should not here. But router 2 should be able to reach its gateway, which it can. And let's see if it can reach the other segment, which is kind of odd. And this actually may be the problem on switch 3. Let's see if turning IP routing on is going to allow it to move the packets. So like I mentioned yesterday, most of the Catalyst iOS versions have IP routing off by default. You do need to turn that on before you do any major layer 3 operations. So if you were doing static routing or any routing protocol, you first need to put IP routing on. Okay, so it could be as basic as this. There we go. So switch 3 was not allowed to do the layer 2 packet rewrite, to move the packets between the interfaces unless the routing process is on. So we should see now on switch 3, when we look at the basic routing table, that we see these two segments as directly connected. So we don't need any static routes, we don't need any routing protocols, because these two segments, VLAN 10 and VLAN 20, are directly attached to the neighbors. Okay, is everybody up to with me up to this point as to what the topology looks like? So right now, only switch 3 is doing any layer 3 routing for these segments, for VLAN 10 and VLAN 20. Now on switch 4, we'll enable IP routing. Actually, it doesn't allow us because I don't have an IP address defined yet. But basically what this would mean would be that if switch 3 were to go down, even though there is an additional layer 2 path between router 1 and router 2, they're not going to be able to reach each other anymore because switch 3 is the device that's supposed to be doing the layer 2 packet rewrite. So for example, let's save the config on switch 3 and look at the basic connectivity between the end hosts. Okay, we can see router 1 and router 2, they do have reachability. Now, if switch 3 goes down, then that connectivity is going to be lost. Because even though the layer 2 path is still there, we could do layer 2 switching over to switch 4. Based on how spanning tree reconverges, switch 4 is not yet configured to do the routing between the segments. Okay, so pretty straightforward design. Right now, there's no redundancy. So what we want to add next is on switch 4, we want to configure it also to route both for VLANs 10 and 20. Between the two switches, switch 3 and switch 4, we're going to have two separate redundancy groups, one per VLAN. So this means that both of the switches will have interfaces in both VLANs 10 and 20. And depending on how we define who is the active router and who is the standby router, that will be the device that actually replies to the ARP requests coming in from the host. So next thing I'm going to do here on switch 4 is add these layer 3 interfaces. I'm going to add interface VLAN 10 with the IP address 10.0.0.254 and interface VLAN 20 address 20.0.0.254. So now while switch 3 is reloading, we should be able to regain connectivity by using this new router that's on the segment. Now what we will see here on router 2 is that even though there's a new layer 3 device in the network, which is switch 4, switch 4 is viable for routing this segment, router 2's packets are still failing because when we look at the ARP cache, router 2 still has it cached in here that this is the MAC address of switch 3. So until the ARP cache, there's a question there, is IP routing not on switch 4? No, I did not turn it on. Okay, so good catch there. We do need to say IP routing. And I actually may be running the wrong version on this switch here. Let me see what switch 3 is running. Now that is the correct version there. Why is it not taking the IP routing command? Oh, I know why. But before, when we were talking about layer 2 networking, and somebody had a question about the size of the CAM table. What I did before was I changed the memory allocation on the switch, and we can see this if we look at the show SDM prefer. I changed it so it was optimized for just VLAN switching. So it says that there's 0 entries that are allocated for the routing table. So some of these platforms, they call this the Switch Database Manager. It allows you to change basically the profile of what the switch is doing. So right now I have it enabled just for layer 2 only, so it doesn't allow me to do IP routing. So I actually have to reload to fix this. What I would need to say is SDM prefer let's say routing. And if we show SDM prefer, we'll see that now there will be more memory allocated for unicast routes as opposed to the unicast MAC addresses. But unfortunately, now I need to reload this device to get there. Okay, so let's go back to switch 3. Switch 3 is reloaded, but we can see there's now an error message. It says there's a duplicate address 10.0.0.254 and 20.0.0.254 on VLANs 10 and 20. So under normal circumstances, the IP addresses do need to be unique in the network. We can't get some sort of hack on redundancy just by putting the same IP address on the multiple devices. Now, they will be sharing the same IP from a virtual point of view, but only because they're going to be using HSRP in order to communicate this. So what we will do now is take these addresses off of the VLAN interfaces, and we're going to put some other address that is unique for the actual assignment. So on switch 3 of VLAN 10, we'll say that the address is 10.0.0.3 for switch 3. But our virtual address from the HSRP process, we'll say standby, we'll give it a number, let's say 1. The IP address will be 10.0.0.254. So technically, this is the minimal config that we need just to get the redundancy group started. We could leave everything else as the default, and we would get basic redundancy. So on VLAN 20, we're going to do the same type of config. The address will be 20.0.0.3. And we want a redundancy group, standby 1 IP. Oops. 20.0.0.254. So this is the virtual address that the neighbors will agree on. Now we can see HSRP does its state transitions. Now there's a couple of states behind the scenes where we're in the speak state. Basically means that you are exchanging hellos with the neighbors. Standby state means that we are exchanging hellos, but we are not actively forwarding. Then finally, we transition into the active state because there's no other routers in the group. So now we are exchanging hellos, but we are also servicing the virtual IP address. And we see this happens for both of the groups, both for VLAN 20 and for VLAN 10. So since we are the only neighbor, we are now active for both of the groups. Now the verification of this is going to be the show standby. So we have two separate groups, one for VLAN 10 and one for VLAN 20. Now I've given them the same group number, which is not an issue because they're in separate broadcast domains. Okay, this message means now that switch 4 must have reloaded, so let's check it. All right, I'm going to do the same thing on switch 4. On VLAN 10, we'll change the address to something that is unique, but we will agree on the standby group number along with the standby IP address, the virtual address, 10.0.0.254. Standby 1 IP. And same thing on VLAN 20. So IP address will be unique. We'll say 20.0.0.4. And the virtual address is 20.0.0.254. So what we should see now is that switch 3 and switch 4 basically form an adjacency with HSRP, that they learn that each other are in, they're sharing the same group. Now we'll see this from either the device's perspective when we look at the show standby. We should see who is the active router and then who is the standby router. So previously it said the active router was local and standby was unknown because that was before switch 4 joined the group. So at this point, assuming that spanning tree has converged, when we look at show standby, it says that we are the active router. Active router is local. Standby router is 10.0.0.4, which is the other device. So this address, 10.0.0.4, is the unique address of switch 4, where our unique address is 10.0.0.3. So we do need this in order to exchange the HSRP control plane traffic. Now what we'll see from the basic configuration of the group, just by defining the IP address, what we are doing is defining the virtual address and the virtual IP address, I should say, and the virtual MAC address. Now the virtual MAC address is always going to start with this well-known prefix 0000.0C07.AC. The last byte, so these last two digits in hexadecimal, this is the group number encoded. Now since we are in group 1, the MAC address ends with 01. If we were in group 10, the MAC address would end with 0A. If we were in 255, it would end in FF. So it's the group number encoded as hex. This ensures that all of the routers in the same group are then using the same MAC address. Okay, there's a question, can we show run? Let's look at the interfaces. I'll say show, just regular show run. Okay, so nothing too complicated up to this point. We just have our unique IP address on each of the VLANs and then the virtual address. This would be identical on switch 4. The exception is it has a unique address. It has 10.0.0.4 and 10.20.0.0.4. Now we can verify this by looking at the ARP cache of any of the devices now. So let's say we go to router 2 and we ping over to router 1. We can see it's successful. The packets that were lost there, that's the amount of time that we need to send the ARP request and get the ARP reply. Now we see what the ARP cache used to look like on router 2. It said that the default gateway address 20.0.0.254, it has the MAC address 0.0.0.f, etc. associated with it. If we look at the ARP cache now, we can see that this has been replaced with the virtual MAC address, the 0.0.0.0.0.CO7 AC01, where 01 is the group number encoded. So now this means that router 2 does not actually know which physical box is forwarding traffic on its behalf. It doesn't know if it's switch 3 or switch 4 because both of these neighbors are sharing the same virtual MAC address. Now, if I were to ping them individually, 20.0.0.3 and 20.0.0.4, and look at the ARP cache here, we'll see that these are their unique addresses. So these are their actual burned-in MAC addresses. Switch 3 has the 0.0.12, switch 4 has the 0.0.0.f. But these MAC addresses would only be used if we are communicating with the public address of the device, not if we're communicating with the virtual address. So at this point, what we should see, we'll save the configs of both of the switches, and we'll do again that ping between router 2 and router 1. And on switch 3, we'll do a reload. Okay, so we're simulating just a complete hardware failure of the active router. Now what should happen is on switch 4, it says we're now transitioning from the state of standby to active, because there was a keep alive interval in which we detected that switch 3 was down. We now take over the active status. And what we should see eventually, and the convergence is going to be a little bit slow. We'll talk about why it is slow here. But eventually, router 2 should regain its connectivity back to router 1. And I believe it's going to take about 30 seconds here, give or take. Let's see if that is accurate. And each of these dots, these are 2 seconds. So 1, 2, 3, 4, 5, 6. So let's take a look at what router 1 sees. Router 1 should be able to reach its own local gateway, which it can. And let's see if it can reach router 2. And you know what? I didn't turn IP routing back on once I reloaded. Okay, so now they have connectivity to each other. So we should see, it actually, the convergence would have been a little bit better than that, but I was missing the IP routing keyword on switch 4. Let's see, switch 3 is back now. So let's try this one more time to look at the convergence. If we look at on switch 4, let's look at the show standby. It says right now the active router is local. This is for both of the VLANs, VLAN 10 and 20. Once switch 3's HSRP process loads, we should see that switch 3 becomes the standby router. it's going to take probably 20 seconds or so after the reboot. Okay, so once switch 3 completely loads, we can see for groups VLAN 10 and VLAN 20, it says we change from speak to standby. So speak is when we're exchanging the hellos. Standby is now where we're exchanging hellos and we're listening for the active router to go down. So switch 4 should be able to see this in the show standby outputs, which it does. It says standby router is 10.0.0.3 or standby router is 20.0.0.3. Now from router 2's perspective, if we were to look at the ARP cache, we can see that there's no difference in what the MAC address associated with the virtual IP is. So from router 1 and router 2's perspective, ideally this should be transparent. So let's try this one more time. I'm going to save the configs. I'm going to ping from router 2 to 1, reload the active router, and we'll see how long it takes to reconverge on router 2. Okay, so if I count these up, these are 2 seconds each. We have 1, 2, 3, 4, 5, 6. So 17 packets we lost, so it's about 35 seconds that it took to converge. Now, if we look at the output from the show standby on either of the devices, it says the hello time is 3 seconds and the hold time is 10 seconds. This means that if we do not receive a hello from the active router within 10 seconds, we are going to promote ourselves from the standby state into the to the active state. In this case, switch 3 is active because the other switch is already down. So we would expect convergence time to be somewhere around 10 seconds, give or take some additional time for the other router to promote itself. But in our case, it was much longer than that. It was 30 seconds plus. So what would you guess is adding the additional convergence time here when the device goes down? Is going to be the spanning tree. So at this point, we have just the regular per VLAN spanning tree default configured. This means that if any link goes down, we basically have to first detect that the link goes down, so that's going to take a few seconds. Then we go through our normal forwarding delay. Listening phase is 15 seconds, learning phase is another 15 seconds. So once HSRP converges, or actually once spanning tree converges, then HSRP can converge. So it's taking us about 35 seconds total. So in the high availability environment, you do need to take both the layer 2 and the layer 3 convergence into account. Now, one way that we could quickly speed this up without having to go through a lot of additional configuration would be just to change from per VLAN spanning tree to rapid per VLAN spanning tree. So we talked about this yesterday. It's the same as per VLAN spanning tree where we are running one instance of spanning tree per VLAN, but we are running it in the with the rapid spanning tree algorithm. So on all 4 of these switches, I'm going to change the mode. We're going to say spanning tree mode is rapid per VLAN spanning tree. Now, also like we discussed yesterday, what else would we want to change here to make sure that we get the fastest convergence possible with rapid per VLAN spanning tree, or just rapid spanning tree in general? Remember, with rapid spanning tree, every time there is a change in the root port, we have to do a new synchronization process downstream. The synchronization process happens out all point-to-point designated ports. That means a downstream facing interface that is in full duplex mode. We look at switch 1 and switch 2. Let's look at show spanning tree for VLAN 10. So in this case, we have the trunk links as defined as point-to-point links, but also the edge ports. So the links that are actually attaching to router 1 and router 2, or basically all of the routers, we would want to make sure to put the spanning tree port fast command on these. Because otherwise, the switches are going to send the proposals out. They're not going to get a reply back in. So they will have to wait the normal forwarding delay before they can use those interfaces. So here on switch 1, I would want to say interface range fast Ethernet 1 and 3, spanning tree port fast. Or actually, in the case of router 3's link, I could just shut that down because it's not being used right now. And I'll actually shut down the other unused ports as well. So on switch 2, I would want to go to router 2's port and say spanning tree port fast. Okay, the other links, I'll shut these down. Because we need to remember in the overall high availability design, each of these small delays will start to add up. So if we are running dynamic trunking protocol, we may have less than a second, possibly more than 1 second to negotiate that link. If we're running Ether channel and we're running LACP or PAGP, it's going to take some time to do that negotiation. Then in spanning tree, depending on the algorithm we're running, if we're using default spanning tree, we may have up to 50 seconds of additional convergence. Then on top of that, we have the time that it takes the CAM table to be flushed out and repopulated, followed by the HSRP convergence on top. So between these two switches, switch 3 and switch 4, the next thing I'm going to modify is the timers between the two neighbors. So the lower the dead interval and the lower the hello interval is for HSRP, it should equate to a faster detection of the neighbor being down, and we'll be able to switch over between the standby and the active router faster. So on both of these links, on VLAN 10 and VLAN 20, we'll say standby 1 timers. Now we can do it in seconds, or we can even do sub-second hellos. I'll say it's as quick as possible. We'll say 15 milliseconds is the hello interval, and then the dead interval, let's say 3 times that. Let's say 45 milliseconds. Actually, the minimum is 50. So we'll do the same thing on both links. Now the neighbors do need to agree on the timers, so we need to do that on everybody. Okay, there's a question. So the hello will go over the Fast Ethernet 19 link, so it won't really impact the traffic. Well, that really depends. If we look at the topology here, we can see that there is a link directly connected between switch 3 and switch 4. And the idea is that we want VLAN 10 and VLAN 20 traffic between the switches to go over that link. Okay, is everybody with me on that point? The basic HSRP control plane, the HSRP hellos, we would want those to go over the directly connected link between switch 3 and switch 4. But what is actually going to control whether that is the link that's actually being used? Because this is a layer 2 trunk link. What's going to control how traffic is forwarded over the layer 2 trunk link? So not only do we need to make sure that the spanning tree is rapid, but we need to make sure that the root bridge placement is correct. So on switch 3, let's look at show spanning tree for VLAN 10 and show spanning tree for VLAN 20. Now, in this case, it just happens to be a coincidence that the network is already working properly, that the root port is faster than at 19. This is because switch 4 already has the lower MAC address out of the 4 switches. But in a normal design, what we would want to do for the next step is to make sure that for spanning tree VLAN 10, switch 4 is the root primary. And the same thing for VLAN 20. So whoever is the active router for that VLAN, we would also want them to be the spanning tree root. Because otherwise we can end up in some weird layer 2 forwarding path that is going to add convergence time to the layer 3 HSRP. Okay, and actually we see switch 3 thrashing between states. What does this probably mean here? That we're going standby active, active speak, speak standby, standby active over and over and over. It actually means that the timers are too low. So these switches, they can't process fast enough in order to exchange the hellos in that manner. So what I need to do is actually raise the hello interval a little bit. Let's say I raise it to 100 millisecond hellos and 300 millisecond dead time. Now we'll see this is also the case when we get to our layer 3 redundancy and we try to do things like OSPF sub-second hellos or very fast timers for EHRP and BGP. Sometimes a design that you think would add more redundancy to the network and make it be able to converge faster, you get down to some hard limit where it's actually a negative onto the network, and the network spends too much time trying to deal with the control plane that it can't actually forward normal traffic. So in this previous case, I was saying the dead interval was 50 milliseconds. The switches are probably doing something else where if they miss the hellos within 50 milliseconds, they have to give up their active status. And we would basically be thrashing back and forth, not agreeing on who is the active router, who is the standby router. So let's check now. If we show standby on switch 4, it says active router is local, standby router is router 3. So probably with these platforms, this is going to be pretty close to the maximum, or to the minimum convergence, I should say, between the two. So let's go to router 2. We'll do the ping, and I'm going to set the timeout to 1 second. So this means that if we see a single dot, then that's going to be 1 second of packet loss. So we will save both of these configs. And then reload the switch. So it was one second. You can see the single loss there. So still, it's fairly quick considering that these are not that powerful platforms. So 3500s, they're more access level switches. But if we're looking at this from a 4500 or a 6500 that has a very powerful supervisor, then it should not really have an issue doing very low timers for the particular group. Okay, there's a question. What does Cisco recommend? Should switch 3 and 4 begin to flop when the traffic? Could they begin to flop when the traffic gets higher? Yes, they could. And that's really kind of a function that would be individual to your particular network design. So you'd have to look at your traffic patterns and then figure out what is acceptable for that platform. Usually what you would want to do is to keep track of like the CPU utilization of the device. If you see that the HSRP process has taken tons of CPU time, it probably means that the timers are too low. Because before you employ these designs into production, you really need to build the whole thing in the lab and then do different testing, like unplug different cables, power off the switch and see what the result is, and see what the final convergence time that it takes. But for these switches, still 1 second is pretty good, assuming that you're on the phone and the phone call is not going to drop within 1 second of packet loss. You may have it where you have to tell the person to repeat what they said, but still it's pretty good overall design. Okay, so any questions up to this point with the basic functionality of the neighbors keeping track of each other? So really the only configuration that we did on the switches was to agree on the virtual address. I changed the timers down to speed up the convergence a little bit. And then we made sure that there were not going to be any layer 2 spanning tree convergence issues. So this is by running either multiple spanning tree or rapid per VLAN spanning tree, and then making sure that the root bridge placement was correct. What I probably would want to do here also would be to go to switch 3 and say spanning tree root VLAN, or spanning tree VLAN 10 root secondary. And same for VLAN 20. So this means that if the active router does happen to go down, then I will take over as the root. Because we want to avoid the case where switch 1 or switch 2 ends up being the root bridges. Okay, so now let's look at some of the advanced functionality of the protocol, which is mainly going to be based on who is elected the active router based on different criteria that we define. So if we look at the show standby output, right now it says the active router is local, the standby router is 10.0.0.4. Okay, the reason why switch 3 is active was because we reloaded switch 4. Now in this case, this design, it really doesn't matter who is active and who is standby, as long as we have the convergence numbers that we're looking for. Now what we could potentially do is say that for VLAN 10, we want switch 3 to be active, and for VLAN 20, we want switch 4 to be active. This would give us some sort of load distribution between the two devices, assuming we're forwarding traffic to the rest of the network. So let's say router 1 is sending traffic to the internet. That traffic would transit through switch 3. And if router 2 was going to the internet, that traffic would transit through switch 4. So we would get at least some crude distribution of the load between them. Now the way this is going to happen for each of the 3 protocols is based on this priority value. So priority is 100 by default, where a higher priority means that you are more likely to be elected the active device or the master router for VRRP or an active virtual forwarder in GLVP. Now also note that it says here that preemption is disabled. We'll talk about preemption more later in the week when we get to OSPF and talk about the designated router election. But basically what preemption being disabled means is that if switch 4 had a higher priority than switch 3, it would not be able to take the active router status away. So again, if preemption is off, whoever is currently the active router will stay the active router, regardless if someone new comes in with a higher priority. So it's meant to be for stability, where you don't have the active router changing back and forth between the platforms. Now, the problem you run into, though, is that if your preferred active router goes down, let's say switch 3 is the preferred active router, it goes down and then comes back up at a later time. Even if it did have a higher priority, it would not be able to take that status away from the current active router. And we can see this in practice easily by going to switch 4. And we'll go to the VLAN 20 interface and specify that for standby group number 1, I want to change my priority to 200. So now I have a higher priority than default. We should be able to see the result of this on switch 3, which we do. It says the standby router now has a priority of 200. Our local priority is 100. But we can see that switch 4 is not able to take the active status away. This is because the preemption feature is disabled. So in most designs, you would want preemption on, and you would want it on all devices in the group, because then they will pay attention very strictly to the priority values that we have configured. So on switch 4, if I say that for standby group number 1, I want preemption on, we can see now we immediately become the active router, because we have the higher priority than switch 3 does. So normally you would want this on all groups. I'm going to put this on both sides. Standby 1 preempt on VLAN 10 and VLAN 20. Now what we will see is that when there is a tie in the priorities and preemption is on, the election is going to be based on the IP address. So we here have 10.0.0.3, which is the lower address. If I were to go to VLAN 10, let's say I change my address to 10.0.0.13, and we show standby. Active router here is 10.0.0.13. If I change it back now, change it to 10.0.0.3, switch 3 should give up its status, so it changes from active to standby. So in the case of a tie in priority and preemption is on, whoever has the higher IP address, they would be elected the active router. We'll see that's the case in a lot of different types of elections, especially when we get to routing. Usually there's going to be some tiebreaker at the end. Whoever has the higher address, they're going to win whatever election is in question. Okay, but I want the design here, again, for load balancing between the two groups. So switch 3 is active for VLAN 10, and switch 4 is active for VLAN 20. And the way I can simply do that is by changing the priority values. So for VLAN 10's group, I'm going to have a priority of 200. For the other group, I have a priority of 100. We can see the result in either case on anybody in their group if we just look at the show standby. So we can see for VLAN 10, we are active because we have priority 200. They are 100. Preemption is on. So it means at any point in time, whoever has the highest priority, they're always going to be the active device. Then for the second group, we are a priority of 100. They are 200. So they are the active router. Now we can actually test this if we go down to router 1 or router 2. And what I'm going to do here is enable telnet access into the switches. So on their VTY lines, I'm going to say no login. That's just going to let the telnet users in. So from router 2, let's say that I telnet to the virtual address of VLAN 10. This gets us to switch 3. If I were to telnet to the virtual address for VLAN 20, this gets us to switch 4. So this was one basic way of testing who is the active router for that particular group. Now, normally in production, you're not going to just allow your users to be able to telnet into the switches, but at least for your basic lab testing, it's one way you can check how the protocol result is working. But again, when we look at the ARP cache of the end hosts, they still have no idea what's going on behind the scenes in the group. They're always going to see this virtual MAC address, regardless of who is actually servicing the virtual IP and the virtual MAC. For switch 3, we have it as the active router for VLAN 10. Switch 4 is the active router for VLAN 20. Okay, there's a question. So was it possible to set the priority per VLAN? It's technically not per VLAN, it's per group. Now, the group is associated with the VLAN, but you could technically have a case where you have multiple groups per VLAN. So what I did here is on switch 3, I said on the VLAN 10 interface, the priority was 200. Then likewise on switch 4 for VLAN 20, its priority was 200. The default priority is 100. So this forces switch 3 to be active for VLAN 10, switch 4 to be active for VLAN 20. Okay, now let's look at the case where we do tracking, and based on different conditions of the network, if certain links are down or we don't meet the conditions of an enhanced object, we can change the priority value selectively in order to get someone else to become the active router. Now, let's say, for example, that on switch 3, we want to look at this link Fast Ethernet 13. Now, Fast Ethernet 13 is going to be our main path that we use to reach router 1. And this would ultimately be based on, it's going to be based on the spanning tree root port election. So let's say also for this case, that switch 3, we want it to be the root for VLAN 10. So under normal circumstances, when router 1 forwards traffic from itself to router 2, we should see that the final forwarding path is going to go to switch 1, to switch 3, to switch 4, down to switch 2, this way. So the interconnects, the diagonal links, those are basically going to be backups. So now what I want to do in this case is to say that if Fast Ethernet 13 is down, I do not want to be the active router for VLAN 10. Because if Fast Ethernet 13 is down, what is the forwarding path going to look like from router 1 to router 2? Well, it's still going to get to switch 1, but now it can't go this direction. So it's going to have to go up to switch 4. If switch 3 is still active, the packet is going to go over to switch 3, but then it's going to have to come back that direction. Then down to switch 2, and then finally down to router 2. So if this link is lost between switch 1 and switch 3, there's going to be some inefficiencies in the forwarding for VLAN 10. So what we could say instead is that if Fast Ethernet 13 is down on switch 3, just take myself out of contention for being the active router for VLAN 10. Send the active state over to switch 4, in which case the forwarding would then look like this. So it would be a more efficient path from the layer 2 perspective. So by adding the object tracking, or by adding the interface tracking, we're trying to avoid a case where a link failure causes a suboptimal forwarding in the network. So what we're going to say implementation-wise is to keep track of Fast Ethernet 13 on switch 1. If this goes down, we want to change our priority from 200 to something that is lower than switch 4's priority of 100. So I'm going to have to say subtract 101 or higher. Okay, usually the easiest way to do this is just to subtract 100% of your priority. Because if we know that we don't want to be the active router when a certain case happens, then we could just subtract all the priority, and we're definitely sure that we're not going to be the active router then. Okay, so let's look back at the command line here. So first on switch 3, I'm going to change it so it is the root bridge for this VLAN. So spanning tree, VLAN 10, root, primary. So now let's look at the forwarding path of the layer 3 versus the layer 2. What I want to know in this point is when router 1 sends the packet to router 2, if I do a trace route to router 2, how does this actually forward from a layer 2 point of view? So which trunk links am I actually going over in the network? And you can see when I do the trace route, the active router does expose itself. So on router 1, let's look at the show ARP. This 0000 0C07 AC01, this is the MAC address I want to know what's going on with this in the layer 2 network. So on switch 1, I need to correlate this MAC address with the CAM table. This is going to show me how spanning tree has made its selection. I'm going to look at the show spanning tree, or not show spanning tree, show MAC address table dynamic for this address. And I want to see it in VLAN 10. So notice it's in the CAM table twice, but that's okay because it's in different VLANs. So for VLAN 10, it says use port Fast Ethernet 16. That's the directly connected port that I would use to reach switch 3. Now, if this were to go down, then obviously we can't use that port in the CAM table. The link is down. So what should happen is that if we look at the CAM table again, it should be refreshed in a new port. Now it's reachable out port 19. Once the link comes back, then it should fairly quickly go back to 16. Because now spanning tree is doing rapid convergence. So spanning tree is pretty much as fast as we possibly can get it. Because as soon as it detects the link down, spanning tree starts to recalculate. So if this link is down, what we want to see is that when router 1 uses its virtual IP address, the virtual gateway, this should say switch 4 as opposed to switch 3. Because we want switch 4 to take over the active status when that layer 2 trunk link is down between switch 1 and switch 3. Okay, so what we need to do on the active router in question, which is switch 3, is we need to configure a tracking instance that is going to look at the line protocol status of this interface Fast Ethernet 013. We're basically going to say if the line protocol is not up, so if it's down, down, or administratively down, we want to subtract a priority value from the HSRP group. So the easiest way to do this is just to go to the VLAN interface. Okay, this is where the standby command is. We'll say for standby 1, we want to do a tracking. And I'm going to track interface Fast Ethernet 0/13. If this goes down, I will decrement my priority by, let's say, 150. My current priority is 200. If I take away 150, I'm going to have 50. That's lower than the other device. And since preemption is on, switch 4 should take over the active status. So it's really 3 things in conjunction with each other that are working. It's that the priority value of switch 3 is getting decremented. That's happening by the tracking. The fact that switch 4's priority is now higher. And the fact that switch 4 has preemption enabled. So if preempt was not on, then this design is going to fall apart. Okay, so now let's try this. Let's go to switch 1. We're going to shut down the link. We should see that now switch 3 says I'm no longer active for that group. I'm changing to the standby state. The end result is that now the virtual router is switch 4. If we look at either of these neighbors and look at the show standby, we can see that the priority of router 3 is now 50. So it took its previous 200, it subtracted 150. Now it's lower than switch 4. So for the final config on switch 3, this is just one command on the interface. Okay, the addition of the tracking. Okay, any questions up to this point? Now the tracking also can be more granular. As I mentioned before, we could do things with the enhanced objects or the IP-SLA agreement. I'm not going to spend a lot of time going through that right now, but we will go through a basic example where we would say, let's say we'll do it with a ping that's going just to a local loopback address. And we could use this loopback to simulate a connection to our ISP. So on switch 1, let me bring that link back up. And on switch 3, I'm going to create a loopback interface. We'll say the address is 3333. So let's assume that this address 3333 is the remote end of our link to the ISP. So if we can ping 3333, we'll assume that our internet connection is up. So what I want to do in this case is that if the internet connection is down, then I want to remove myself from the active status and have someone else do the forwarding. So first step, we're going to create the IP-SLA instance that is going to do the pings to the destination. So in global config, we'll say IP-SLA, create an instance number. Now we define what type of tracking will this be. Now, depending on the individual iOS version you have, you'll see higher level platforms and newer versions are going to support more operations. This particular case, a 3550 with 12 to 44 advanced IP services, you could ask a DHCP server for an address. You could send a DNS request. You could try to download a file from FTP or get a page through HTTP, send an HTTP GET. Path echo, path jitter, UDP echo, UDP jitter, those are going to be for voice over IP testing to see what is the delay on a circuit. So if you have a managed service provider that's giving you IP telephony transit, we could say, if you go above 100 milliseconds latency, then I need to perform some action. In this case, I'm going to do just an ICMP echo. This is just a basic ping. So we'll say ICMP echo, destination is 3333. How often do I want to send the pings? We'll say the frequency is every 3 seconds. And the timeout is going to be 1,000 milliseconds. So I'm going to ping them every second, or excuse me, I'm going to ping them every 3 seconds. I should be getting a reply within 1 second. So then there's a lot of other granular stuff you can get into. You can say, what's the threshold that you need to go past in order for the operation to be declared down? So I could say, how many pings do I need to miss in order for it to report the error case? But for this, let's just use the defaults. We're saying ping them every 3 seconds. Timeout is 1 second. The address I'm pinging is 3333. Okay, now I'm going to start the instance. Say IP-SLA Schedule instance number 1, I want to start it right now. And the lifetime is going to be forever. So indefinitely now, that instance is going to run. Now from this, we can do some basic verifications by looking at the show IP SLA. And there's a lot of different verification here, but I want to see what are the statistics. It says right now for instance number 1, the latest round trip time was 1 millisecond, which you would expect because we're pinging our own internal software loopback. But it says right now the latest operation return code is OK. So this is really what we're looking for. Basically anything that says not OK is going to be considered down. So if the return code is timeout or the return code is unreachable, pretty much anything that is not OK means that the instance is going to be down. Now we could check this if I went to the loopback and shut it down. Then I said show IPSLA statistics. We'll see now the latest return code is timeout. So this is simulating a failure to our ISP link or whatever we're trying to track. Okay, now once the loopback is back up, return code is OK. Okay, next we need to tie this SLA instance into the HSRP process. And we're going to do this with what is known as an enhanced object. So from global configuration, we create a tracking object. We'll say it's object number 10, okay, whatever local number that we decide. I want to track a response time reporter entry. Entry is number 1. Okay, this number is basically the IP SLA instance that I created. So we could configure some more detail here. We could say how long before you report the object down. In this case, I'm just going to leave all of the defaults. So now if we look at the show track, it says track object number 10 is checking the response time reporter 1 state. Last return code is OK. The state of the object is up. Okay, this means that the pings are happening fine. If I went to the loopback and shut it down, then looked at the tracked object, now the tracked object is down. Once the loopback comes back up, now the tracked object is back up. Then last step here, we're going to tie this to the HSRP process. So on interface VLAN 10, I'll remove the previous tracking statement, and we'll say standby 1 track, object number 10. If object number 10 is down, I want to decrement my priority by 150. So our final verification for this, if we look at the show standby, it says that for group number 1 on VLAN 10, our current priority is 200. We're tracking object number 10, which is currently up. But if this goes down, we're going to subtract 150 from our priority. Final result is going to be that switch 4 should take over the active status. So if we look at this from router 1's perspective, when we telnet to the virtual router, we can see router 3 or switch 3 is active. If we shut down the loopback being down causes the SLA instance to go down, which causes the tracked object to go down, which in turn decrements our priority in HSRP, causes switch 4 to take over the active status. The result we would see from router 1 is now that switch 4 is the active device. So as you can imagine, you can get very granular with the types of checks and balances you want in here. and it can extend up to the application level. So the ping, the ICMP ping, is good just for basic reachability testing. So then, actually what this is really good for is a lot of access DSL environments, because what you'll see a lot of the times if you're using DSL for your router to get to the internet is that the DSL circuit could be down, but your local Ethernet interface stays up, because we're not looking at an end-to-end layer 2 keep alive over DSL. Because DSL is basically bridging between Ethernet and ATM. So if the DSL circuit goes down, the router on the access end, it doesn't know that. So by adding the IPSLA instance, you could just say ping the other end of the DSL circuit. If I don't get an ICMP echo reply back in, then I'll perform some action like taking myself out of the HSRP group or changing my static routing. Okay, so here's our final config for this type of design. We have the SLA instance. It's saying ping that address every 3 seconds. Timeout is 1,000 milliseconds. The tracked object is saying take a look at the SLA instance number 1. HSRP says take a look at the tracked object number 10. So if track 10 goes down, decrement our priority by 150. That gets us to be lower than what the other side is. Okay, any questions on any of the first hop redundancy protocols or the examples that we looked at here with HSRP? Now, like I mentioned, the Catalyst switches, the lower end platforms like the 3550 here, 3560, these will not support VRRP or GLBP, but you could try out the same type of example on a normal router, and you would be able to use those in its place. So pretty much you'd have the same exact syntax here, except it would say VRRP1 or GLBP1. Okay, so real quick before we get into our next topic for Layer 2 security, the other portion of the blueprint, which relates to high availability here, is, like I mentioned before, the intra-chassis redundancy. So redundancy between your route switch processors or between your supervisors within one of the individual switches. So this would prevent the case where if one of the supervisors just goes down or it loses power, you should be able to switch over to the other one, and it's not going to affect the forwarding, and it is not going to affect the other neighbors. Okay, the way that this works is through a feature that is called non-stop forwarding or non-stop routing. Now, what non-stop forwarding does is decouple or separate the control plane of the network from the data plane. Now, the control plane is where we handle our management protocols like the OSPF adjacencies or the EHRP adjacencies and the routing information that is exchanged between those two neighbors. The data plane is the actual line card that is that forwards the traffic. So this would be the physical Ethernet port, the copper RJ45 interface, or the fiber optic interface that you have on the platform. So it's basically separating these into two discrete portions, where in the case that the control plane goes down, it is not going to affect the data plane. Now, in most non-modular platforms, like the switches we're looking at this week, if the CPU just died, then packet forwarding is going to stop. Because the control plane and the data plane, they're basically the same thing in this type of platform. But in the higher level platforms, we have the separation between them. So if the brains of the switch or the brains of the router goes down, that's the RSP, it's not necessarily going to stop the forwarding. What it will do instead is switch over to the redundant processor, either the redundant supervisor or the redundant route switch processor. But in the meantime, the goal is to continue forwarding packets without having to have a traffic black hole, or without having to have any packet loss. So the key is we need to figure out when we're actually doing this switchover. It's going to take some amount of time here to switch over between the route switch processors. So how do we deal with this? Okay, this is what the stateful switchover, the SSO, and the nonstop forwarding is designed to fix. So the configuration for stateful switchover is very, very straightforward on the platforms. It's usually just one command like set high availability enable. It's more of a hardware thing where you need to make sure that the supervisors have the same code revisions and they're identical hardware in the platform. But once we have it configured, basically the data plane, which is going to be like the CEF table, the actual information that's used for forwarding the packets, that's going to be shared equally between the two supervisors. So if one of them goes down, we still have the old information cached. In the meantime, the control plane will restart on the new routing engine, so the new supervisor or RSP, and tell the routing adjacent neighbors, so the BGP peers or the OSPF neighbors or the EIGRP neighbors, tell them, do not declare me down. I am going through what is known as a graceful restart for nonstop forwarding. So this type of signaling that is done by the Interior Gateway Protocol, the IGP, depends on the individual protocol. EIGRP uses something known as the restart bit. OSPF uses link local signaling, or the opaque LSA. BGP negotiates the graceful restart capability. But the theory behind the three of them is going to be the same. That when the supervisor goes down, the main forwarding engine goes down, you tell your adjacent neighbors that I'm switching over to the new route processor, so you're going to need to send me the routes again. You're going to need to re-cache me the information. But it does not declare the EIGRP adjacency down, the OSPF adjacency down, or the BGP peering. So it's a combination of the layer 3 protocol's intelligence. This is where the nonstop forwarding happens. And then the actual layer 1 switchover, which is the stateful switchover, the supervisor redundancy. So within the scope of the exam, you basically just need to know what this feature is. You wouldn't be tested on configuring it, because it's not really a configuration. It's more of just a hardware capability that you have the proper modules to do it. But as long as the routing protocol you're using is enabled for the feature, so for example, OSPF has link local signaling on by default, and it will automatically try to negotiate nonstop forwarding. So if the platforms do support it, then it's not going to be a problem. You just need to make sure you have the redundant supervisors or the redundant RSPs.